Can you hear me? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Screen is visible?
Yes,
Yes,
sir.
sir.
Okay, let me start. Well, I want to teach you Bayes category theorem, but I taught you last semester. Whatever I taught you, that I will teach, so that I'm just going to have a revision of that Bayes category theorem. Okay. So you should again look at the note. I have uploaded, but same thing what I did last semester. So this is, I just want to explain again Bayes category theorem. I will give a question on Bayes category theorem in minor. So that idea you need here, basically no word tense. Already we have got a dense set. That means if you have a topological space X tau dense, then suppose A is a subset of X and A bar equal to X, then A is called dense, or some people called everywhere dense. That is not required. That dense is enough. Everywhere dense. Okay. Some people call it everywhere dense. Okay. But we are interested in nowhere dense. Okay. So suppose A is called, A is a subset of X called nowhere dense. Okay. Nowhere. It is not only the interior. If interior of A bar is empty. Be careful about A bar. A bar is important. This is called nowhere tense. Okay. And if not equal to, it is non-empty, then it is called somewhere tense. Don't use the term somewhere tense. Okay. So it's called nowhere tense. So this is very important. It's enough for to understand Bayes category theorem and apply. Application of Bayes category theorem actually is very simple. So it is enough to know this is nowhere tense. Okay. The first proposition I left in exercise, I have given equivalent characterizations of nowhere tense. This actually you will get in Alipranthisi. They didn't prove separately, but in the discussion they said A is nowhere dense. They wrote this way, nowhere dense. That's my equivalence of A and B. If and only if K is nowhere dense, if and only X minus A bar is dense. If and only if this. Look, A is nowhere dense is same as A bar is nowhere dense. If you take bar of A bar, that will be A bar. X minus A bar is dense in X. This is basically representing the term. When you prove it, that whether if it is nowhere dense, then you cannot have this. You just take a point that will violate this thing. Okay. You should remember that interior of A bar should be, A bar is closed, so this is open. Okay, so interior of A bar should be inside of that. Okay, so now the thing is, so A and B can immediately prove, only the fact is C, but it is not difficult to see that. C actually equivalence of A and C is required usually if you want to prove more advanced results in Bayes category. In this note, I'm not going to do that, so that Don't need to bother much about it. Okay. So that now just example again I am repeating the example I did in the last semester. Like if you take this Q set of rationals, look int Q bar is it R, which is R. So this is not no advance. Q is okay, not no advance. On the other hand, okay, you see that if you take any point here in a metric space, okay, forget about metrics, just take this, take any point here. Then you see that interior of X bar, since every singleton is closed, basically for that you need only T1 is 5 because it doesn't contain any intervals. So any singleton is no advance. Any singleton in is no advance. Okay, so that can I find other examples also. Okay, so it's no advance. Now look, Q is not no advance, fine, but Q can be written as like this, where each Q is no advance. That means it can be written as countable union of no advance set. In topology, countable actually is a small thing. Countable union of no advance sets. So this is important. If it is no advance already, it's fine. But if it is not no advance, whether a set can be written like this or not, this is the question. That is related to Bayes category theorem. So here you have, I'm coming to the Bayes space later on. I'm taking first category set. First category. First you have defined no advance, that I told you, no advance. Now suppose you are having extra topological space. A subset of X. Then A is called a set of first category. Basically thin set, some people call it thin. So these are called set of first category. They are also called mega set. That means not much is there inside. Some people call rare set or thin set. But last two terms are not usually used often. This is also used, this mega set. If A can be written as a countable union. This is very important, not any union. Countable union means either countably infinite or finite. Union of nowhere dense sets. Okay. So you need to know what is first category. If it can be written as a countable union of nowhere dense set. So what I just got, Q is a set of first category. In, it is important, in where? Think about it, what kind of category? What category? What category Q has in this? Think about it. Q has in this. So it is first category if it is countable union of no attention. Second category if it is not first category. In topological space you have only two categories of sets. One is first category, that is defined, and if it is not in first category, then it's second category. Second category. If it is not the set, it is not of first category. It is not of first category. Okay, right? So what does it mean? That means suppose how we actually apply Bayes category theorem. Suppose you have X tau, the topological space. Look here, I don't need any metric space. All these things related to nowhere dense, that you can define any topological space. You don't need metric space. Though I was giving some example from R, but you don't need to be metric space. It is done. It can be done in general topological space. So suppose you have this, and suppose you have the information A is of second category. Suppose you have this information. This is a hypothesis you have. Sub second category. That's the application. Next semester you will get in function analysis. Suppose I can, now you have this. Somehow you get this. While working with topological space, you get this. Okay. So it will mean, first you are getting countable union of sets. Okay. That means it implies there exists n naught such that interior of a n naught bar not equal to phi. Because reason is very simple. If you do not get any such n naught, that means every set will be nowhere dense. That means they will be countable union of nowhere dense. That will be of first category. So this is usually we do. We try to prove that. Now how will I know it is second category? That is another problem. Okay. Somehow you have the information A is of second category. Then whenever A can be written this, you must have this. In fact, your work starts after this, because this means what? This means you get this, which means what? X is an interior point. Then that means there exists a neighborhood of X which will be contained until inside A naught. That means there exists a neighborhood U of X in X tau such that this, don't think, I'm not saying, because you have got this, so you have this bar. Okay, sometimes you may have this close, that is a different thing. So this you will get, and for that you will work with this. Okay, that work you will work with this. Then after that you work with this. That is good enough. So this is the way you use second category. Now, what is Bayes category theorem? That I will tell you. But before that, let me tell you what is Bayes space. That in page 142 here, definition 4.3, Bayes space. Okay. X tau is called a Bayer space, a topological space. I'm not assuming any separation action, but usually people assume at least house drop. But that's the separate thing. X tau is called, look, no separation axiom is assumed here. It's called a Bayer space. Bayer space. If, look, careful, has to be every non-empty open subset, that is open set in X, open subset of X is of second category in X. Look, here I'm being specifying. I'm emphasizing because in a subspace it may change the category. Okay, I know about these things, but I didn't want you to learn all these things and that. If you want, I can give you a good reference on that. Just where you can just read about Bayer spaces. Second category in X. This is important. Not any subspace. Okay. Right. Like I told you about, you can think of that Q. Okay. Well, in fact, the other thing is question. I'm just telling you, it's called second category. Every non-empty open set. Of course, empty set we do not bother. You can think of that if you want. What will be the category of empty set? But empty set, no. Non-empty set, open subset is of second category. Every. In fact, here is a question why I'm emphasizing. Suppose you have X tau y subspace topology. That is y is a subset of X. Okay. And suppose you have non-empty set. Then question you can ask whether category is preserved. Is the category of a preserved? That means something I can like question. A is of first category. In y tau y. That means if and only if this is a question. A is of first category in X tau. This is a question. I'm not going into that question. I'm just raising it because this you should be careful. This is second category in X. It is not in the subspace. That you should be careful. Okay, right. So here to answer this question, you see sometimes a dense sets. If you have dense subspace, then probably you get some affirmative answer. Okay, right. So that second category. Every non-empty open subset of X is a second category. Look, it's a definition, fine. Sorry. But the point is that how, suppose given question is now. Given a topological space, X tau, how to determine if X tau is a paired space or not. So apparently that will be an application when you are going to apply. That will be a big issue. Okay. That will be a big issue. You say, okay, I will find an open set, which is, suppose, negative answer sometimes is easier to find, negative answer. Suppose negative answer means sometimes easier, I'm saying. If you find an open set, non-empty open set, which is of first category, if you find the non-empty open set of first category, in next, then by definition itself is not a bare space. Then X tau is not a bare space. I'm saying it's easier in a sense, little bit, may not be always easy. Suppose from the given topological space and the structure of the topology, you can find out, you can figure out one open set, of course non-empty, which is of first category, then it's fine. But positive answer, that means you really want your space to be a bare space. How to determine it's a bare space? How to determine X tau is a bare space? Okay, that's the answer is given by theorem 4.2. Okay, before remark you should, if X tau is a bare space, then by the definition, X is of second category in itself. In itself means in X tau, that is in X. Because X itself is a non-empty open set. If X tau is a bare space, then X itself is a non-empty open set. So it should be of second category. Usually write second category in itself. In itself means that is in X. Now theorem 4.2, I put the star mark. I give the complete proof. You should read the proof. Okay, I'm not going to give you the proof here, but the proof you should understand. Make sure that the theorem 4.2 is one big help. Theorem 4. How it is big help? First of all, this proof you should read. Now look, basically you look at theorem 4.2, equivalence of A and B. C is also there. Sometimes C helps. C, D also helps. Look, C is complement of any set of first category in X is dense in X. Complement is also dense. Okay, right? First category set. Well, first of all, look at A implies B. I'm not going to give you the proof. What B says. B says intersection of any sequence of dense open sets is again dense. That means B, the statement of B. If you take a sequence of open sets, open first of all, open set in X tau, each of them, dense in X. That is, so open dense implies this. This is also dense in X. For any, not only one, the intersection of any sequence means countable family of open sets, open dense sets, open as well as dense. Obviously, its intersection may not be open because you know that finite intersection of open set is open. Arbitrary intersection open set may not be open, but we are not concerned about that. That's why we are saying only this intersection will be dense. The intersection will be dense. So this is B is sure Be careful to understand. It's easy to understand. Unless you want to complicate it, you can't do it. It is very simple statement. Okay, so you have this. In fact, often in proving that X is a bare space, we use this thing. Use this. That's why you say if you use this thing, then why we don't use it as a definition of bare space? Some people use it. Some people use it. Some people use, some authors use B as the definition of bare space. Because practically, often we use this to prove it a bare space. Well, you can say that, but historically, definition we have taken, historically that should be the definition. Isn't it? First idea of first category, second category came. First. Then later on people realize that and look in the definition we are giving in terms of second category, that is category of sets. And bare space that I told you that name bare space was given by later on by other French mathematicians. So it is not due to bare at all. It is I told you last semester this is Osgood, an American mathematician. He in some analysis work he used it 1897. And then bare used same thing in 1899. But result what I'm saying, definition what I'm saying, that is due to Hausdorff. Hausdorff space you do it. That is 1913, 14. Okay. So that way this space should be called Osgood bare Hausdorff space, not bare space. So don't right now don't be concerned about the name to the space. Concerned about why this definition is given, because historically first we started this category of sets and then we came and then we saw that. Then people also realize that whenever you do something space, you give something, then how to apply, implement practically on ground. That is very important. You give me nice things, nice results, but then when you try to apply to verify your species has this thing and not, then you say it's a very troublesome to prove it. Then it is of no use. So theorem 4.2 from that viewpoint, it's very useful. Okay, that's why if people do not want to go into the category thing, they usually take B as the definition. Okay, look here, I don't need to talk about category. Okay, right, intersection of any sequence of dense open set is again dense. So that's the, but I will suggest you don't need to mug up. I won't give in the exam, but you should read the proof of this. It is written all very clearly that you should not have problem, okay, in understanding these proofs. Okay, A implies B, B implies C implies D, D implies A. You should prove, you don't need to mug up. Okay. In fact, in remark, whatever I was shouting, the remark I have put that many authors use the equivalent condition B of theorem 4.2 as the definition of a bare space. Okay, right. Now in Adipratis Barkinshaw Z, many other books you'll see they give the first result this theorem that every complete metric space is a bare space. Okay, I have given something a little bit generalized that I will tell you. First of all, you see that it's a big result. That's why I told you last semester, if you have a metric space, the first question you should ask, is it complete? Here is one such reason. Is it complete? Because if it is a complete metric space, it will be a bare space by this result, and then you can do many things, both in analysis and topology. By analysis, I mean real analysis, function analysis, both, even complex analysis. Is it complete? That's the question. Given a metric space, the first question you should ask yourself if it is complete. So here we have this vital result that every complete metric space is a bare space. So if your metric space is complete, you know it's a bare space. Okay. Now the thing is that how the proof is given here. Okay. You see that the what Ali Perkins gave, and that basically they have used Cantor's intersection theorem. Okay. I'm telling you that they have to prove that basically you need this thing, Cantor's intersection theorem. Remember last time I told you that Cantor's intersection theorem is important in the sense it helps us to prove other big results. Okay, on its own, it may not be important, but it is very important in the sense it helps us to prove other big results. The Cantor's intersection theorem, you see what is that? If XD is a, though converse can be proved, but usually the well-known version I am giving, XD is a complete metric space. And suppose you have this decreasing sequence of closed sets. This way, decreasing means this. I think major theory you are also doing using this notation. Decreasing sequence of closed sets. Not only that, such that in metric space we have defined diameter. So the diameter of Fn goes to 0 as n tends to infinity. Decreasing sequence of closed sets. Such that this, but this is important. Then intersection Fn is non-negative. In fact, you can prove first with this, it cannot have more than 1 point. That is immediate. It cannot have more than 1 point. But here, that is important thing. We're saying it will have a point, unique point, basically, a singleton. This is a singleton. So that's the Cantor's intersection theorem. This is very important. Okay. So Cantor's intersection theorem is used here. But here in the proof, so they start with a complete metric space and then start proving it. But look, if I take completely metrizable and metrizable, let me recall that. Completely metrizable and metrizable. These are definitions used for topological space. X tau is called metrizable if there exists a metric D such that D generates tau. That is, look, tau D is a notation, means the topology generated by D. Don't confuse with this tau, equal to tau. Okay. If your topology comes from a metric, that we have seen, if you have a trivial space with more than 1 point, that cannot be generated by a metric, because metric space every singleton is closed. You need to, it is a house draw. Okay, In fact, we have seen already many things that a metric space is Tychonomy. A metric space is normal. So if a space is suppose not normal, even T1, T2, but not normal, it cannot be metrizable. Okay. So completely metrizable means if there exists a complete metric. If there exists a complete metric D on X such that this is tau D equal to completely metrizable. Metrizable, completely metrizable. There may be spaces which are metrizable but not completely metrizable. Not completely metrizable. Now look, in the proof, the Alipranthes-Barkinson they gave, it's a nice proof. They started with a complete metric space, but the same proof, now look, same proof I can use it. But it will be a much stronger result. That I am going to tell you that I am writing this. Every completely metrizable space, every completely metrizable space, X tau, topological space, is a paired space. Look, what will be the difference between the two proofs? On the first line, you will see since X tau is a complete, you will write X tau since, here for the proof, X tau is completely metrizable there exists a complete metric. The Baird space, I'll have to prove that every non-empty open set is of second category. I am not changing the open sets. I am keeping the open set same. That's why the concept is the metrizable. There exists a complete metric D on X such that degenerates the topology tau. So you will work with, now you work with xt. That is the proof they have given. xt. This is a complete matrix. But eventually you are coming back, open set you are taking that open sets are the same. So you are proving open set, every non-empty open set is of second category. Okay. So this is the proof. That only thing I have, right? But it is very important. That's why. It is more powerful than this. Why? Look, last semester I taught you, you can look at the note again, that minus pi by 2 and pi by 2. This. Okay. This is with usual distance metric, it is not complete. But here you should have the idea of the homeomorphism. Look, if you have this, suppose, now let me, before talking about this result, look at this result. That you should prove. Let fx tau y sigma be a homeomorphism. Okay. A. If x tau is metrizable, so is y sigma. So is y sigma means y sigma is also metrizable. That means metrizability is a topological property. Is a topological property. B. If x tau is completely metrizable. So is y sigma. That means this will be also completely metrizable. This you can prove. Only thing, suppose it is metrizable. The first thing I am telling you that actually the proof will be the same. Only thing, one extra thing you'll have to prove that if you have a complete metric here, you will get a complete metric here. Suppose tau is generated by tau t. Now I want to give a metric here. I need to give a metric here which is generate the same topology. Then how will I do it? Well, look, I can define row y1, y2. Look, it's a homeomorphism. So it's a bijection, one-to-one correspondence. So what I'll do, define P F inverse y1 is a singleton, defined, well defined, and F inverse y2. Where it got D, this. Suppose tau is generated by the metric T. Then you give this. Look, basically it is coming in isometry so that you can easily check rho is a metric because D is a metric there. Rho is a metric on Y. All you'll have to check, rho gives you the same topology. How do you show that? That sigma is tau rho. Look, though I am using notation tau, it means the topology is standard notation generated by rho. You pick up an open set here, show it's open here. You pick up an open set here, so that means you show this. Okay. And you can easily check after you getting this part is tricky. This after you get this, then you can prove that if D is complete, okay, then rho is also complete. If T is complete, then rho has to be complete. Basically, any Cauchy sequence will transfer here. Since D is complete, it converge here. Then you come back to this Y, that will converge to the image. Okay. So that complete metrizability and complete metrizability, they are topological properties. So that did I prove this or talked about this? I think it is another chart that I didn't upload. That isometry between metric spaces you have. Oh, here you have it. Result. Page 145. I left it an exercise. Yes. So that now the advantage is that exactly I said that here. So here I said that. Yes. Now look at this. So this I stated already. So that now look here. This is not complete, but on this, if you give this metric rho xy, sorry, if I give this that I said that rho xy equal to tan x minus tan y. This is a metric, and this will give the same topology. But actually, how do I get? I get by the result. Basically, look, what I'll do that here I take this. F, the angle you will get, so that take fx equal to arc tan x, that means tan inverse x. Okay, fx equal to take tan inverse x. You can check that f is a homeomorphism. Look, if you take f inverse, that means f inverse y, if y belongs here, that will be tan 1. Yeah, don't confuse with xy. It is there. If you want, you can take this thing. Let me write it. Okay. So that exactly is coming. What I explained in the result. F is a homeomorphism. But this is metrizable. So this is metrizable. This is completely metrizable. So this is completely metrizable. So if you just try to apply with that result, every complete metric space is a bare space. Well, look, that's a sufficient information, not necessary information. Then you will be lost. You may not conclude that with that result. You won't be able to conclude that whether it's a bare space or not. But if I have the result, every completely metrizable space is a bare space. Since this is completely metrizable, so it is a bare space. This is a bare space. Because you should check that in complete metric space, you can have another complete metric which will give you the same topology. So that is another thing you should look at. So it is a bare space. It is a bare space. That's the advantage of my result. That completely, my result means what I am saying, that observation, that every completely metrizable space is a bare space. Every completely metrizable space, so that you should remember the result this way. Every completely metrizable space sometimes I used to give the question to ask the student whether this is a bare space or not. They will happily write it's not a bare space because this is not a complete metric. But what I am giving this is a bare space. Because this can be put into homeomorphism with the interval, open interval minus pi by 2, pi by 2 is a bare space. Is a bare space. So that don't forget about. And if you have special case complete metric space, you already know it is completely metrizable. Then it's of course it's a bare space. Okay, right? Use the map that I told you that. Everything I'm just explaining that. Okay, so that, and here you'll see that to prove this, actually we have used Cantor's intersection theorem. First I'll say there will be a metric, complete metric D, come with this, and then finally prove that, look, why we use Cantor's intersection theorem? Because we do not use the definition of bare space. That I told you in that theorem, we use the condition B, theorem 4.2b. That means we want to show that if you have a family of dense open sets, countable families, sequence of dense open sets in X, I need to show by taking in the metric, completely metric, I am not changing the open sets. This is dense. Index. That exactly we prove. So use this thing. We do not prove straight. We use this thing, and just because it this to prove now, prove this, we use this. Now, in order to prove this, we need Cantor's intersection theorem. How? That I'm going to tell you. Cantor's intersection theorem. Okay. So, look, first of all, when you say the dense, suppose A is dense. A is dense means what? I already explained. A is dense if and only if every non-empty that I've used in both direction in the proof, every non-empty open set U intersects E. Well, if you have take a bar equal to x, then every point of x is a closure point. So if you take every non-empty open set U, you take a point, but this is a neighborhood of x. At the same time, this is a closure point. X belongs to U and x belongs to a bar. So by definition of the closure point, this will be this. Where if you take any non-empty open set, intersect A, then you take a bar equal to x, then you take any point, you'll have to show that a bar equal to segment any non-empty set intersect. That is the statement here. You take any non-empty open set containing x, by this it is intersect, so this will be this. So in fact, though it is simple to derive about dense set, you should remember this. Every non-empty open set U intersects A. This we use to prove in both directions. That you should read the proof. Make sure you read the proof. So every completely metrizable space is a Baire space. Every completely metrizable space is a Baire space. Well, look, I can always pick up techniques. Look, I told you last time that techniques are important. More important than the results. So when you look at the proof, in some sense, I say the proofs are more important, because in the proof you understand that why your result is coming, why something else won't come. So that in the proof you understand, you learn about the techniques, and that is why when you even if apparently you have a big proof, if you are to produce it somewhere, if you want to see how it comes, that's the way the mathematicians work out. Basically, you need to look at the sketch of the proof. Sketch of the proof. That will be probably 3-4 steps, and each step then you will elaborate. Usually it will be 3-4 steps. That is in the sketch you have, and those things you need to elaborate. Then you will get the complete proof. Same thing you can see here, that every completely metrizable space is a Baire space. So that I'm giving you the exercise, that theorem 4.3. You should, because I can give you a problem where you'll be using the technique, not the result itself. Theorem 4.3, proof. You don't need to mug up. Read carefully. If you understand each and every line, you should thank yourself. You should congratulate yourself. Okay, read yourself. Okay, and try to understand each and every line. Okay, I have written very simple way in that. You should not have problem. Okay. I have given the historical perspective also. Yes, that I forgot. In 1897, the American mathematician Osgood showed that any countable intersection of dense open sets in R is again dense in R. That is the problem. Osgood didn't connect directly with the Baire space, so-called definition category. In 1899, Baire proved this result for n-dimensional Euclidean space. In 1914, Hausdorff went one step further and proved that every completely metrizable space has the property that any countable intersection of dense open sets in X star is again dense. This is the result we have proved. This result eventually came to be known as the Baire's category theorem. Baire's category theorem. The term Baire space was introduced by Bourbaki. Look at net for Bourbaki. You can go to Wikipedia. Strictly speaking, theorem 4.3 should be called Baire-Osgood-Hausdorff theorem. Now let us go for some exercises. I have given some exercises here. So these exercises you should, I think you did last semester, because Bhavna told me that if people got all the tute problems twice solved by Bhavna and other one, the pattern, and that's why you did well in major exam. That's fine, but don't think topology will be that easier. You have the wrong conception. Okay, make sure that you do all these problems. Okay, right? So that Baird's category theorem, that now look here, what the example Baird's category theorem basically we usually, now let me tell you the last thing. Baird's category theorem. Actually, this is Baird's category theorem. Every completely metrizable space is a Baird space. But often in application, use corollary 4.4, and we say that we can say that by Baird's category theorem. We don't need to say that by a corollary. This, look, if X star is a completely metrizable space, okay, then X is of second category. I'm assuming, suppose you are completely metrizable. Let me write this thing. By this result, this is a Baird space. The X itself a non-empty open set. So, since this is a Baird space, X is of second category in itself. That means in X star. Actually, we use this thing often. So that X is of second category, matlab kya hai? That means if you have this, that I was telling you. Whenever you have this, there will exist a knot such that you will have this thing. 99.9% time you use, whenever you say by Baird's category theorem, you use this corollary. Okay, that is, you should understand. That moment you say it's a Baird space, so this is of second category. In this, you may ask, if that is the case, it is quite possible you can have a space of second category. That means I am using only very restricted thing. Only X is of second category. I don't need to know about other open sets. I need to know about other open sets. Is it possible that you have a second category space, but which is not a Baird space? This is true. Still, I will have this thing. So that's why it is called Baird's category theorem. We are interested only second category. So that this tells you that raises the question. Does there exist a non-Baird topological space X tau such that X is of second category, they are non-Baird, but X itself is second category in itself? This is a question. Answer is yes, you can find. So that means Baird's category theorem is also known as, this corollary is also known as Baird's category theorem. So when you apply one to Baird's category theorem, we are applying very narrow thing. That X is of second category in itself. That is possible. Okay, think about it. Think of it. I'm just leaving it an exercise on that. Anyway, I would like to mention my PhD supervisor, he had a research monograph on pair spaces. That is published by actually Banach Center. That will share the name often. Warsaw. Actually Warsaw. This is for the Polish language. So, but in English you will see that. Poland. Definitely, Stefan Banach was one of the, if not the, one of the highest ranking mathematicians. Very few mathematicians could parallel him, could parallel his ability. So I just think about it. Any country other than Poland where you can find an institute. This is a research institute, Banach Center, which is named after a mathematician. After a mathematician. Here in India we have Harishchandra Research Institute, but HRI, Bilawad. But you will be surprised to know when it was founded, its name was not HRI. Name was something different after a non-mathematician. It was changed later on. Okay, Harishchandra Research Institute. You can look at who is Harishchandra. I think they talk about Ramanujan, but after Ramanujan, I think Harishchandra was the great Indian mathematician. Right. So second category that I told you, that you can think of that. Okay. So I think I finished it. Well, in next class I will talk about the syllabus will be up to, let me tell you, syllabus, I just to tell you, up to pairs category theorem. Up to this. But let me tell you that which things you should read. I have taught you a lot of things in the sense, a lot of concepts in that. So that first thing you should read first countable and second countable space. This you should must read first countable, second countable space. B, you should read about T1 space, T2 space, Tychonoff space. In the node even I didn't talk about regularity in that. So that's for your information. Tychonoff space, normal space, 54. That you should read. C, product space. I have given the finite product, but if you are comfortable, you can think about product of 2. But you should understand here they would give the topology in terms of the basic open sets. Basic open sets. So basic open set will look like this, where U is open in X, V is open in Y. So product topology you should understand. And here you should understand if you have a function fx tau to, then we have the graph of f. This is very important in function analysis, particularly. It is important everywhere. X fx. X belongs to X. So this is a subset of X cross Y. The graph, graph is a subset of X cross Y. It may be closed, may not be closed. So if graph is closed, if f is continuous, it can be proved easily. You can take the net. F is continuous implies graph is closed in X cross Y. When you do not mention anything, this is topology, product topology that I told you. But the question in the other direction, this is not true in Jan. Graph may be closed without being continuous. Okay, right? So that I have given you example, y equal to 1 by x. X not equal to 0, I take x equal to 0, you can take 1 or 0 if x equal to 0. Okay, this has got closed graph but not continuous at 0. Okay, so that so closed graph need not be, if you have a function as closed graph, then it need not be continuous function. So that closed graph, it is closed graph means this is graph is closed here. So that you may think of that there is a gap. That gap may be filled up in many ways. Okay, so that it is related to that. This is a weaker version of continuity. It is not coming continuous. You can say that weaker notion of continuity, closed graph. Okay, so that you should do. Think about that. When the product topology comes in analysis, when you're doing it, that's the comes through closed graph. Okay, right? And of course, basic things you can do it. Suppose x and y are first countable, whether x cross y will be first countable. If x and y are both second countable, y whether x cross y will be second countable. Okay, so next thing I've taught you, right now also talk homeomorphism, that you should recall the definition. I forgot what, how many I taught. A, B, C, then D. D, homeomorphism. You should read. And E. Where's 8 minute? देखता हूँ क्या लिखा. First counter, second countable product space. It's fine. Homeomorphism. Where's category theory? Okay. And quotient space. I have given note from Willard that pictures and that how the quotient space comes. Okay, right. I think this much I taught you on that. Okay, right. Bayes category homeomorphism quotient. Let me check that. This is one. I will try to cover all these things and that. There will be 6-7 problems, probably 40 marks. So make sure that. So here is another set of problems here that you can ask Saurabh, and I have given already this. I have taught you that, but that you did last time. Make sure that you do this problems also from Ali Francis workings. Now I can finish that. What is it? Wait a minute. Yeah, paired space, delta set. Yeah. Yes. Thirty, 14, 15. But another thing should be there. What is there? Just trying to find out. Couldn't find out. Oh, number 6. Okay. Yeah, this much you can do it. Okay. So I'll send you the when I'll take the class tomorrow or the Friday. But I'll send you the notice later on. Okay. Make sure that if you have any problem, you can ask Saurabh, you can ask me by email on that. Okay. Or in the next class. I hope to take at least one more class before your exam. And another thing I would like to tell you that you should fix a date during the exam week, not after that, because then you will miss my lectures and other people's lectures, and particular other teachers, they will complain to me. So that you should fix a date during the exam week, that is preferably next week. Okay, so 23rd, in a way it is not acceptable to me right now. Okay, so you should give a date during the next week. Okay, sure. Bye.